Pakistan Air Force got stomped in Operation Sindoor. You know why? Those cocky PAF dimwits thought the Indian Netra AWNC was still rocking that old gallium arsenide radar with its shorter detection range. Surprise, motherfuckers. India had secretly upgraded that shit to the latest gallium nitride tech, massively boosting the range, power, and performance. Oh boy, the IAF tag team that upgraded Netra with the S-400 air defense system and absolutely fucked the PAF. They lit up Pakistani jets and even an AWNC bird from ridiculous distances, dominated the skies, and left Pakistan begging for a ceasefire after getting their asses handed to them. India dictated the fight, degraded PAF's awareness, and turned their invincible air force into a smoking punchline. Operation Sindoor was a brutal reality check. Former DRDO Chief Dr. S. Christopher recently confirmed that the latest Netra Mark 1 already carries gallium nitride technology in its active electronically scanned array radar. This upgrade has moved from laboratory work into actual aircraft. The change gives the Indian Air Force better eyes for watching vast areas of air and sea. The familiar Embraer-based jets now see farther, track sharper, and operate more efficiently than the first versions. The original Netra Mark 1 used gallium arsenide transmit-receive modules. Those modules formed the backbone of the dorsal balance beam antenna that scans 240 degrees. Each module sent microwave pulses and listened for echoes bouncing off aircraft, drones, missiles, or ships. The material has a band gap of 1.42 electron volts. That energy gap sets how much voltage the device can handle before electrons avalanche and cause breakdown. In practice, engineers kept drain voltages between 8 and 15 volts. Power density stayed modest at half a watt to 1.5 watts per millimeter of gate periphery. Efficiency usually fell between 25 and 40% during radar pulses. Thermal conductivity measured only 46 watts per meter Kelvin, so heat built up fast inside the array. The system still delivered solid performance with detection ranges around 250 to 300 kilometers against typical fighter-sized targets. It worked well in real operations and gave commanders a useful picture of the battle space. Now the latest Netra Mark 1 brings gallium nitride into those same modules. This wide band gap semiconductor changes the physics at the electron level. The band gap reaches 3.4 electron volts, more than double that of gallium arsenide. Breakdown electric field climbs to roughly 3.3 megavolts per centimeter, about 8 times higher. That property lets engineers run the transistors at 28 to 50 volts. Power density jumps to 5 to 10 watts per millimeter. The same physical space inside the dorsal spine now radiates several times more radio frequency energy toward the horizon. Because the radar range equation depends on transmitted power raised to the 1/4 power, this boost stretches detection distances noticeably. Standard search modes reach toward 350 kilometers, while super extended settings push beyond 475 kilometers under good conditions. Deep inside the device structure lies the real magic. Gallium nitride high electron mobility transistors usually grow on silicon carbide substrates. An aluminum gallium nitride barrier layer creates strong correlation charges at the interface. These charges pull free electrons into a thin two-dimensional electron gas channel. Sheet carrier density hits 10 to the 13th per square centimeter. Electron saturation velocity approaches 2.5 times 10 to the 7th centimeters per second. The channel conducts current with low resistance even when high voltage appears across the drain source terminals. Transconductance stays high. On resistance drops, the result is efficient power amplification across the frequencies used in airborne early warning radars. Power added efficiency moves comfortably into the 50 to 65% range for typical pulse duty cycles and waveforms. Far less prime power from the aircraft generators turns into waste heat. Thermal management tells another deep story. Gallium nitride on silicon carbide spreads heat at 130 to 490 watts per meter Kelvin depending on layer quality and substrate thickness. Junction temperatures remain lower even during sustained high power transmission. Self-heating effects that cause pulse droop or gain compression stay controlled. Thermal resistance from junction to case drops dramatically compared with gallium arsenide. Cooling airflow or liquid systems inside the aircraft can run at lower capacity. That saves weight, reduces fuel burn, and gives designers margin for future growth. Modules packed denser without thermal runaway risks, the entire array maintains consistent performance across long patrol durations at altitude where outside air is thin and cold. Pulse stability reaches another level. Gallium nitride devices showed trapping and dispersion effects from surface states and buffer layers. Engineers counter this with careful epi-layer design and bias sequencing. A short gate bias preconditioning pulse applied just before each radio frequency burst creates a warm-up drain current. This brings the device into a quasi-steady thermal and charge state. Amplitude variation and phase jitter fall by 10 decibels or more. Pulse-to-pulse stability easily meets the minus 55 decibel requirement needed for effective moving target indication and Doppler processing. Clutter cancellation improves. Slow-moving targets or formations stand out clearly against ground returns or weather. Operators inside the Netra cabin see cleaner screens and trust the tracks more. At the array level, the gains multiply. Each transmit-receive element radiates stronger pulses with better phase accuracy. Effective isotropic radiated power rises significantly. Digital beamforming algorithms steer the energy with finer resolution and lower side lobes. Instantaneous bandwidth widens because gallium nitride supports broad matching networks without sacrificing gain or efficiency. Frequency agility increases. The radar hops across bands or uses spread spectrum techniques to burn through jamming while keeping high output. Low radar cross-section targets become easier to detect because the illumination energy is greater. A target with 1/100th the reflective area of a fighter jet can still return a usable echo at useful ranges. Stealth fighters, cruise missiles, and small drones lose their advantage of late detection. Let us look closer at the radar equation. Received power equals transmitted power times transmit gain times receive gain times target radar cross section times wavelength squared divided by 4 pi cube times range to the fourth. Increase transmitted power by a factor of 5 through higher power density and you gain roughly 50% more range for the same minimum signal to noise. Everything else equal, that means earlier warning. Hypersonic threats or sea-skimming missiles give away position with more reaction time for interceptors. Fighter pilots receive cueing vectors sooner. Surface-to-air units prepare launches with greater standoff. The entire kill chain gains breathing room. Power handling inside the module also improves reliability. Gallium nitride tolerates high voltage standing wave ratios better than gallium arsenide. Reflected energy from damaged antenna elements or unexpected impedance shifts causes less stress on the final amplifier stage. Graceful degradation becomes practical. The radar continues operating at reduced but still useful performance if some modules fail. Combat survivability rises. Maintenance crews replace individual line replaceable units without taking the whole aircraft offline for long periods. Signal chain benefits flow downstream. Stronger raw echoes improve signal to noise before analog to digital conversion. Receivers capture data with higher dynamic range. Digital signal processors run constant false alarm rate algorithms with relaxed thresholds yet fewer false alarms. Track while scan modes update hundreds of targets simultaneously. Doppler resolution sharpens because phase stability stays high across the coherent processing interval. Integration with electronic support measures and communication intelligence sensors becomes tighter. As-if accuracy from the main radar helps correlate passive detections into single fuse tracks. Mission computers inside the cabin build a rich battle space picture and share it through secure data links to fighters, ground stations, and other Netra aircraft. One platform multiplies the effectiveness of the entire network. Development did not happen overnight. Experience from gallium nitride work on fighter radars like Uttam provided the foundation. Engineers adapted the transmit-receive module designs for the lower frequency bands and longer pulse lengths, typical of airborne early warning. They optimized impedance matching networks for specific pulse repetition frequencies and duty cycles. Environmental qualification covered temperature cycling from ground heat to high altitude cold, vibration during takeoff and turbulence, and altitude effects on cooling and power supply. The latest Netra MK1 already flies with these upgraded modules. 6 additional airframes will join the fleet carrying the same technology. Larger Mark II platforms on Airbus A321 bases will take the concept further with wider coverage approaching 300 degrees and even longer ranges. From the material science view, gallium nitride offers more than raw power. The wide band gap reduces thermal generation of carriers so leakage currents stay low even at junction temperatures approaching 300 degrees Celsius. Devices maintain performance across the wide temperature swings of airborne operations. Reliability models predict longer mean time between failures. Logistics teams stock fewer spares. Aircraft availability climbs without heroic maintenance efforts. These factors matter when the fleet must maintain continuous patrols across diverse Indian terrain from mountains to oceans. Electron transport physics adds depth. In the two-dimensional electron gas channel, mobility reaches 1000 to 2000 square centimeters per volt second. Although lower than gallium arsenide in bulk, the high sheet density and velocity combine for superior current handling. The Johnson figure of merit, which multiplies breakdown field by saturation velocity, favors gallium nitride heavily. That predicts better power frequency performance for radar applications. Cutoff frequencies support the X band and nearby frequencies used in these systems while delivering high output power. Practical waveform flexibility increases too. Gallium nitride amplifiers handle long pulse compression schemes without excessive droop. Linear frequency modulated pulses pack more energy while preserving range resolution after matched filtering. Doppler processing extracts finer velocity bins. Weather penetration improves in selected modes because operators can choose frequencies that balance attenuation and resolution with the extra power margin. Adaptive processing changes waveforms on the fly depending on the tactical situation. One moment the radar searches long range with low pulse repetition frequency. The next it focuses on track while scan with higher update rates, all without hardware swaps. Dr. Christopher highlighted a milestone that reflects years of patient work by scientists and engineers. The latest Netra MK1 already operates with gallium nitride radar. This gives India extended reach today while bigger systems mature. Stronger signals travel farther, faint echoes return clearer, heat stays managed, efficiency rises. The aircraft works harder with less strain. Common people can understand it this way. Your country took a better semiconductor material, engineered it into aircraft radar, tested it thoroughly, and put it into service. The result means better warning, better coordination, and stronger defense of our airspace and waters. Each upgraded Netra sortie covers bigger volumes with clearer vision. Commanders gain richer data for decisions. Pilots receive timely support. Adversaries face reduced chances of surprise. This gallium nitride integration inside Netra shows how material science directly strengthens national capability. The technology rests on measurable improvements in band gap, breakdown field, power density, thermal conductivity, and electron transport. Those numbers translate into extra kilometers of awareness and extra seconds of decision time when they matter most. The fleet will grow. More Mark 1A aircraft join. Larger Mark II versions follow. Each new jet builds on the same gallium nitride foundation. India watches its skies with increasing strength and self-reliance. Steady progress like this builds real confidence. The Netra Mark I with its new radar stands ready, scanning the horizon with sharper, stronger eyes made possible by deep science applied to real-world needs.